Momentum as a vector in this video. So as we've discussed before, a momentum is a vector, which has a magnitude and a direction. When dealing with collisions in one dimension, this isn't a great concern, but most objects move in at least two dimensions in the real world. So we have to take into account that vector addition for conservation of momentum. For example, let's think about two balls colliding. The two balls will move away after the collision in different directions. And here's a diagram of it. This is the first ball. It's going to go towards the second ball, and this is before they collide. During the collision, the first ball and the second ball are going to meet. After the collision, they are going to go their separate ways. Maybe the first ball will go this way, the second ball will go this way. Just like a game of pool. So this means we need to consider both the x and y directions. Momentum will be conserved in both the x and y directions separately. So here's an example of momentum as a vector. I'm going to call this P, and the direction is some angle. Let's just say P is 25 kilograms times meters per second, and our angle is 40 degrees. And then let's find the x and y components. Just like how we would find our vector components when we did forces, this will be the same sort of thing. Because our angle is relative to the horizontal, to calculate P of x is going to be cos of that angle multiplied by our vector. In this case, it's going to be P cos of 40 degrees, and Py is going to be P sine 40 degrees. So doing this calculation, it'll be 25 cos 40 and 25 sine 40 for the y. Px is 19 kilograms times meters per second, and Py is 16 kilograms times meters per second. For our notation, we're going to consider Px to be the initial momentum in the x direction. Py is going to be the initial momentum in the y direction. And like the last lesson, if you want the final momentum, we're going to indicate this by a prime. And if it's in the x direction, it's going to be Px prime. In the y direction, it'll be Py prime. For the conservation of momentum, we can indicate this as delta P, which is 0. Or we could also say delta P is P final minus P initial, and we know that's 0 as well. So if we want to apply this in the x direction and the y direction, this is the x direction. Delta Px is the final from Px. We indicate that as a prime minus the initial Px. And lastly, in the y direction, so delta Py is a change in our momentum in the y direction. So that'll be our final y, indicated as P prime y, minus Py, which is our initial. We know that this would be 0. So we're going to go ahead and do an example of this. A hand grenade weighing 1.2 kilograms is at rest and explodes. 3 pieces move off horizontally, one of 0.5 kilograms to the north at 3 meters per second, one at 0.3 kilograms at 4 meters per second at 45 degrees south of west. What is the mass and velocity of the third piece? The first thing we're going to do is find the mass, because that is the easiest part of the question so far. We know that our hand grenade has been split into 3 pieces, so then there's 3 smaller masses to consider to add up to the whole mass of that grenade. The mass of the grenade we know is 1.2 kilograms. The first mass is 0.5 kilograms. Our second mass is 0.3 kilograms, and we don't know what the third mass is. So all I have to do is rearrange this and solve for our third mass. So our third mass is 0.4 kilograms. And that's one answer. The next thing we're going to do is organize your information and find the initial and final momenta. We are going to consider this in the x and y components. So we're going to consider mass 1 first, and remember that this was 0.5 kilograms. We're going to look at its initial momentum and its final momentum. So initially, we're going to start at rest, and this occurs for all 3 masses because it says in the very first sentence, a hand grenade is at rest. So our initial is going to be just 0 in both directions. So I'm going to indicate our first mass as P1x because this is the first mass out of 3. Then it says this mass of 0.5 kilogram moves north at 3 meters per second. We don't have a horizontal direction, so I'm going to say that's 0. But we do have a vertical direction. Remember, P is M times V. So that M is 0.5, our V is 3 meters per second. So our momentum is going to be 1.5 kilograms times meters per second. Now we'll look at mass 2. Remember that this mass is 0.3 kilograms. Again, for initial, we are starting at rest. I'm going to say this is the second mass now, so P2x is 0, P2y is 0. For our final, I'm going to indicate this as P2x the prime, and for a y, P2y. So looking at our vector from the original question, 4 meters per second at 45 degrees south of west looks something like this, which is relative to the horizontal. So that means to find the x component, we are going to use cosine. And because it's south of west, these are both in the negative direction for both our x and y components, so it's going to be negative for both of them. For x component, we're going to have 4 cos of 45 multiplied by the mass, which is 0.3. Then for our y direction, we're going to use sine, so 4 sine of 45 multiplied by its mass. So we have negative 0.85 kilograms times meters per second And same thing for our y component. Lastly, we'll consider our third mass, which we know is 0.4 kilograms. This has started from rest as well. It's going to be P3x and P3y are both 0 because we start from rest. Now for our final, this is what we want to find. We don't know what these are yet, but we also know momentum is conserved. So we can solve for P3x if we just find our total momentum. So this is our third step. We're going to find the total, initial, and final momenta. Well, for initial, it's pretty easy because if we add up all of them, we're going to get 0 because P1x is 0. If we add P2x with that, that's still 0, and P3x, that's 0. Same thing with our y, because initially we started at rest. So P1y plus P2y plus P3y are 0. So that was our initial momenta in the x and y component. Now we're going to look at our final. So Px prime is going to be P1 x prime plus P2 x prime plus P3 x prime. P1x, looking back at our charts of information, is going to be 0. P2x was negative 0.85 kilograms times meters per second, and we don't know what P3 x prime is yet. Now we're going to look at Py prime. So that would be P1y prime plus P2y prime plus P3y prime. P1y prime was 1.5. P2y prime was negative 0.85. And P3y prime is what we're looking for. I'm just going to simplify this a little bit. It's 0.65 plus P3y prime. Then our next step is to set our momentum so that they are equal. So that means our change in momentum in the x direction is our Px final minus Px initial, and we know this is 0. Same with our y. The change in momentum in the y direction should be your final momentum in the y direction minus the initial momentum. And I'm just going to replace it with what we just found in part 3. So Px prime was negative 0.85 plus P3x. If we were going to subtract our initial momentum in the x direction, we found that as 0. And we know that this is equal to 0. can rearrange and solve for P3x, which is positive 0.85 kilograms times meters per second. Then we're going to look at our y direction. The py prime was 0.65 plus p3y prime. This was found again in step 3. We know this is subtracted by the initial momentum in the y direction, and we found that as 0, and this whole thing is equal to 0. Then we can solve for p3y prime. Which is negative 0.65 kilograms times meters per second. Now we have our x and y component for p3 prime. So now we can combine into one vector. So our x component's positive, our y component's negative, so it's going to go down. We are looking for p3 prime. So using our vector addition, we're going to calculate this using Pythagoras. Be p prime 3x all squared plus p3y prime all squared. Which is 0.85 squared plus negative 0.65 squared. You get 1.1 kilograms times meters per second. Now we have the magnitude. Now we want to find the direction. We're looking for that angle right there, which is tan inverse of p3y prime over p3x prime. Which is 0.65 over 0.85, or tan inverse of that. And this is 37 degrees. I'm just going to say this is below the positive x-axis. Looking back at the original question, we didn't need p3 prime as our final answer. We needed the velocity of it. So that's what we're going to find as our final step. So for our third mass, to find the velocity, if we already have the momentum, the final momentum of our third mass, this is calculated as m3 times the velocity of that third object, its final velocity. We have p3 prime, we have m3, so I'm just going to rearrange this and solve for v3 prime, which is our final velocity for our third object. So I'm going to divide both sides by m3. That's 1.1 divided by 0.4, which is 2.7 meters per second. And we have the direction. We found that in part 6, which is 37 degrees below the positive x-axis. And now we're finally done with that question. It's a long one. We can do one more example with you. So two balls collide. Before the collision, one ball was at rest and the other was moving east at 5 meters per second. After the collision, the first ball was moving 3 meters per second at 30 degrees northeast. What was the final velocity of the second ball? Both balls have masses of 2 kilograms. So it's fairly similar to the last question. I'm just going to draw a diagram of what is happening. So our first ball is approaching the second ball at 5 meters per second. Then after our collision, one ball is going north of east or northeast, and the other one is going somewhere else. So if I want to analyze the vector of our first ball, it's going to look something like this. And if I want the x component of that, it's going to be 3 cos 30. If I want the y component, it'll be 3 sine 30. Again, this is for our first ball. The first thing we're going to do is look at each of these two masses in its x and y component for momentum. For the initial and then for the final. So we'll look at our first mass. For the first ball. So for our px, we are looking at 2 times 5 initially, because it's moving at 5 meters per second and it has a mass of 2 kilograms, which is 10 kilograms times meters per second. Then for in the final, we have the information from our vector already, diagram above. So this is going to be our mass, which is 2, times 3 cos 30. And this is 5.2 kilograms times meters per second. You also need to look at its y direction. So initially our first ball and the y direction just is not moving up or down, so it's just 0. And then for our final for the first ball, use our diagram. So that will be mass times our direction for a velocity, which is 3 sine 30. And that's 3 kilograms times meters per second. Then we're going to look at our second ball. This is starting from rest. So we know initially is both going to be 0. And this is what we're looking for. We need to find px2 prime and py2 prime. Now we're going to look at total, initial, and final momentum. So for our initial, we're looking for px for the total thing, which is going to be our first momentum in the x direction plus the second momentum in the x direction. This was 10 kilograms plus 0. So overall, our momentum in the x direction is 10 kilograms times meters per second. So that was our initial. Then for our final, it's calculated as P1x prime plus P2x prime. This was 5.2 plus P2x prime. I'm just going to leave it as that for now, and then we'll look at our y direction. So initially, in the y direction, we're going to get 0 plus 0. Then in our final direction, we have 3 plus py2 prime. Now we're going to find our missing pieces. So we're going to do the change in our momentum in the x direction, and then we're going to also find the change in momentum in the y direction. So to find the change in momentum in the x direction, this is our final, px final, minus px initial. And we know this is equal to 0. From above, we found that it was 5.2 plus P2x prime minus 10. And this is still equal to 0. Then we can solve for P2x prime and rearrange, which is 4.8 kilograms times meters per second. Now look at our y direction. The change in py is py final minus py initial, and this is supposed to be 0. Py final is 3 plus py2 prime, and then minus our initial py, which is just 0. So I'm going to rearrange and solve for p2y prime. And this is negative 3 kilograms times meters per second. So we finally found the two components. Now we want to find the overall resultant of that. So I'm just going to draw this as a vector diagram. In the x direction, it's positive. In the y direction, it's negative. So it's going to go down. And this is the vector we're looking for. We're just going to use vector addition, in this case, more specifically Pythagoras, to help us figure out what P2 prime is. So that will be p2x prime all squared plus p2y prime all squared. p2x prime is 4.8. p2y prime is -3. Once we solve for this, p2 prime is 5.7 kilograms times meters per second. Now we're going to find the direction. We're looking for that angle, so it's opposite over adjacent, or p2y prime over p2x prime, which is 3 over 4.8. That's 32 degrees, and this occurs below the positive x-axis. The very last thing we're going to do is find our velocity, because that was the original question. So we're going to relate this with momentum, which is p2 prime is equal to m2 v2 prime. Rearrange and solve for v2 prime. So p2 prime was 5.7. The second mass was 2. Our final answer is 2.9 meters per second as our velocity, with a direction of 32 degrees below the positive x-axis.